This tutorial will demonstrate the use of the segmental template in CSI Bridge. This template allows for the rapid modeling of segmental post-tension bridges using either balanced cantilever or span-by-span construction techniques. The use of the segmental bridge template allows for modeling of bridges using cast-in-place segments, or precast segments. Our tutorial will create a balanced cantilever cast-in-place bridge. We will now start our model. On the new model form, we will use the segmental template. This template can significantly reduce the time needed to model segmental post-tension bridges. The quick segmental bridge template form is where the layout line length is specified, as well as basic bridge properties. Our bridge will have a total layout line of 200 feet or 2,400 inches. Our actual bridge will be 160 feet long and will be cantilevered off a single pier. We have a number of choices for the bridge section type, and we will use the AASHTO PCI ASBI standard section. Clicking the Modify Show button, we can review the specific properties of this deck section. If some modification is required, we could click the Convert to Editable Section button, which would then allow for property edits. The last items on the form are used to specify the post-tensioning material and load pattern. We will leave as is for the time being. On the segmental bridge span assembly form, we have three discretizations. The first is the span at the start abutment. The second is the balanced cantilever span. And the last is the span at the end abutment. Although we are doing a balanced cantilever with a single pier, we could also do span-by-span construction. And if so desired, we could add additional discretizations using the various Add and Insert buttons. We will use the three discretizations as shown. The start and end abutment segments are each 20 feet or 240 inches long, and we will not alter these. However, we are going to modify the length of the balanced cantilever segment. Currently, the bridge has a total length of 200 feet, and we will shorten it by 40 feet. 20 feet off each span. We do this by clicking on the Span Discretization Plus button. On the Segmental Span Discretization Definitions form, highlight the Balanced Cantilever 1 segment and click the Modify Show button. On the form, verify that the span type is set to balanced cantilever. The downstation table is on the left, and the segments upstation from the pier are shown on the right. Starting from the pier centerline, each side has a rigid segment 60 inches long. Next are the pier tables, 120 inches on the left and 60 inches on the right. We are going to make them symmetric, so we'll modify the table on the left to 60. Next are CIP or cast in place segments, 6 at 120 inches on the left and 7 at 120 inches on the right, followed by one last 60-inch CIP segment on the left. We are doing a cast in place model, but could also do a precast segmental model. We are going to remove CIP segments from each side, and again we'll make them symmetric. On the left, change the 6 to a 5, and click Modify. On the right, change the 7 to a 5, and click Modify. We will delete the last shorter CIP segment on the left. The length of the balanced cantilevers on each side is now 720 inches. We are now done with this form. Note that the total bridge length is now 1,920 inches or 160 feet. Clicking the View Renamed Segments button shows all of the segments that make up the bridge. The nomenclature used throughout the table is shown on the form. For example, SA and EA for start and end abutments, D and U for down and up stations, and the various prefixes. The user may alter these if so desired. In this area of the form, we can set the support labeling. Perhaps rather than starting with 1, we start with 5 and go in the downstation direction. See how the labels change. We can also specify the span numbering, but we will use the defaults in this model. The segments can be identified by color, which the user can switch on and off if desired. On the table, the first segments deal with the start abutment, denoted by SA. There are 2 cast-in-place segments and 1 closure strip. The next group of segments define the downstation balanced cantilevered segments from the pier, a total of 5 segments. The next 5 segments deal with the pier. 2 pier tables, one at the downstation side and one at the upstation side. 2 rigid segments, and the pier itself. The next 5 segments define the upstation balanced cantilever segments. The last segments define the segments associated with the end abutment as identified by the EA prefix, and again include a closure strip. Once we are satisfied with the segment definitions and verify that the total length is correct, 1,920 inches or 160 feet, we can click OK. The bridge deck is now displayed. Based on the discretizations we've just defined, the program has automatically generated groups, which will be used in the erection sequencing. We can review these groups by going to the Bridge tab and clicking Groups. Looking at the groups, we can see the correlation with the segment names in the previous table. such as PT for the pier table, RG for the rigid segments, and SG for the cast in place segments. Highlighting P01 SG01D and clicking Modify, this is the first segment downstation, which has a length of 10 feet and ends at the pier table at station 840. Switching to the Home tab, we will take a quick look at how the groups are assembled to create the bridge. Using the Select by Groups option, we will select the same P01-SG01D group. We see that it is just downstation of the pier. If we select the next group, we see that it is just upstation, and so on. If we move to the end of the selection list, we can see the groups that are used at the start abutment. The next step will be to define the post-tensioning tendons for use in the model. On the Bridge tab, click the Pre-Stressed Tendons button. On the Define Segmental Bridge Tendons form, select Segmental Cantilever from the Categories drop-down list. We will start by defining the cantilever tendons, and then click the Define Segmental Tendon button. Here we are going to use the autofill option, and will mirror the tendons about the center line of the deck. This powerful feature will automatically generate the layout of the tendons for each segment. Clicking autofill, note that we now have a total of 12 tendons, with 2 anchorages for each segment and pier table in both the downstation and upstation locations. A reference plan for the top slab is shown. If we select the Show Mirrored Tendons option, we can see the layout to each side of the center line. And we can also see the work point. To adjust the tendon parameters, click the Add Modify button. Note that we currently have only a single tendon parameter, T-param1. Here we can review and edit parameters as needed, including tendon area and the loss parameters, such as those due to friction and the long-term losses. We will set the load pattern to pre-stress, and we are going to change the material property. We will add a property of A416 grade 270. We are also going to revise the tendon area based on a quick and somewhat approximate calculation. We are going to use a tendon with 8 strands of 0.6 inch diameter. We will also revise the duct diameter to 2.99 inches. And the tendon load to a stress of 202.5 KSI. We leave all other parameters as shown. While still on the cantilever tendons definition form, we can click the Select Tendon Duct Template button to review the layout of the ducts. Returning to the defined segmental bridge tendons form, note that there are now a total of 24 tendons, 12 distributed to each side of the center line. Show all tendons again shows the plan layout, and scrolling through the cross section shows how they are clustered around the webs. However, these are just the cantilever tendons. Typically, continuity tendons are needed as well. So next, we will add some additional continuity tendons for placement in the bottom span. We will define a new tendon by making a copy of our first tendon, T-param1. Our new tendon will use 4 0.6-inch strands. Again, all the tendon selections are somewhat arbitrary at this point, simply to show the process. They have not been determined from strength requirements. With the first span selected, we are going to add a tendon that runs from the start abutment segment all the way to the pier table using our new tendon. Again, we are replicating about the center line. We will add a second tendon that starts and ends one segment shorter on each end. Switching to span 2, we will replicate the tendons just added on the upstation side. Again, the tendons are added symmetrically. Closing this form, note that 8 tendons have now been defined for the bottom span. Clicking the Show All Tendons shows the location of these continuity tendons. We could also add continuity tendons for the top if needed. The model now has tendons. Next, we will move on to the scheduling. On the Bridge tab, go to the Erection button and click Traveler. Travelers are needed to support formwork for cast-in-place concrete. Note that two travelers have been defined, one for downstation and one for upstation. To see the properties of the traveler, click the Modify button. The traveler weighs 20 kips and has a stiffness of 50 kips per inch. This means it will deflect 1 inch for each 50 kips of load. The eccentricity defines where the center of gravity of the traveler lies relative to the end of the supporting segment in the longitudinal direction. Positive is away from the free end. We will not alter these values. Next, we will click on the Schedule wizard. Here we can set the time required for each stage in the construction schedule, from constructing the foundation and pier to the time required to cast and stress a segment and then launch the traveler, which in our case is 4 days. We will not change any of the duration settings. We can also specify how the segments are to be erected, one by one or in pairs. We will erect the segments in pairs. On this form, we can also set which traveler is downstation and upstation, and specify any additional structure loads, such as wearing surfaces and barriers. Click the Generate Schedule button to generate a detailed construction schedule. The schedule is broken down into 4 primary operations. First, the cantilevered portion of the bridge at the pier. Second, the non-cantilevered structure, that is, the end abutments. Third, the closure segments. And fourth, the time-lapse analyses. Each operation shown in the table is also graphed in the adjacent Gantt chart. Expanding the operations, the schedule starts with the foundation and the pier, then the pier table, then adds the travelers, then starts the casting of the segments. Note that the typical cycle is again 4 days, 80 to 83 on the schedule, and that 4 tendons are tensioned in each cycle. The travelers are advanced, the segments are cast, and all 4 tendons are stressed. As a side note, although we have not adjusted any of the program-generated durations, these may be edited, and all operations that are descendants of the edited operation would have their timing adjusted accordingly. The construction of the start and end abutments occurs early in the schedule, while the closures are constructed late in the schedule. The last tendons being stressed are the continuity tendons in the bottom slab. Once we are satisfied with our detailed schedule, we can click OK to save it. We will next move on to showing how the program takes the scheduling information and generates the load cases needed to perform the analysis. On the Analysis tab, select the Wizard Scheduled Load Case and click the Modify button. From the scheduler, the program has created a nonlinear stage construction load case with a total of 51 stages. Again, the typical cycle is that the travelers are set, a 2-day time-lapse stage while the segments are placed. The next stage adds the segments and loads them. Another time-lapse stage for the tensioning, and the tendons are added and loaded. Changes cannot be made to this load case because it was generated directly from the schedule wizard. As a last step prior to running the analysis, we will look at the erection sequencing of the segmental bridge, which can be done using the Show Tree button. Here we can see segments being cast and then post-tensioned, as well as seeing how the travelers move. With that, we are now ready to run the analysis. With the analysis complete, we can display the deformed shape for our stage construction case. We can step through each stage. Note that the travelers are shown with straight lines. We will also display the force diagram for our stage construction case. This time using the F11 component. This concludes this tutorial on using the segmental template in CSI Bridge for modeling segmental balance cantilever bridges.